So I just started recording. So if you don't want your face recorded, please or just mute your video. Yeah, whatever, you know what I mean. So I'm going to start sharing and let's get this presentation rolling. Okay, can I get a thumbs up to see if people can see my screen? Okay, dope. Okay. Okay, got my polls ready, got this ready. I think we're recording. All right, so just one more check. Everyone can see the presentation. Thumbs up or thumbs down? Thumbs up, sweet. All righty, so welcome to the electrical overview of Mark V. We're gonna just talk about some stuff that we didn't really get a chance to cover in depth yet at this point in the year. I'm excited to share this knowledge because I think it's super important and valuable for everyone on the team. So let's go over the key ideas. So first, I want to answer these three questions. What needs to happen in order for Mark V to turn on? Then how do we go, like go forward? And how do we stop? And hopefully by answering these three questions, we can answer this fourth question, how do all of our boards fit together? And a little disclaimer here, it might not be every single board on the car, but it is a good indicator of most boards. Okay. So this is the block diagram. Just soak it in. There's a lot of stuff on here. And I think if you just stare at this for maybe 3 or 4 hours, you'll get a better understanding of how Mark V works. And that's really all I had for you today. So thanks for attending. If you have any questions, feel free to just send them in the chat. Yeah. Okay, jokes aside, let's break this down a little bit. So you might remember this is how we started out the actual school year. Let's just take a look around. So first, let's look at these red lines connecting everything. The red represents the grounded low voltage system, or the 12 volts. It comes from our low voltage batteries and powers most of our boards on the vehicle. And we also have a CAN bus, which is how our enclosure to enclosure communication really happens. It's most of our board to board communication. If you watch Lucky's presentation, you'll know why we use CAN, because it's super robust, great for the noisy environments that we subject our electronics to. So yeah, we see that on a ton of the boards, maybe not all of them. Next, we have this purple wire, the shutdown circuit. I think I called it the oh shit circuit a while ago, just kind of getting the point that if something goes wrong with the vehicle and we want to turn it off, the shutdown circuit will activate. And it's not really expressed 100% accurately over here. And we're going to dive into this super in depth today. So you'll see why this isn't quite accurate. But just know, if we want to turn off the vehicle because something bad is happening, we have the shutdown circuit. And then, like, really the heart of the vehicle is the high voltage system. That's what drives the motor. It's basically what makes our vehicle move at all, because we need to deliver a lot of power to move. Cool. So I just want to start with a quote, and it says, "The first step towards getting somewhere is deciding that you're not going to stay where you are." And that really doesn't have much to do with Mark V, but I think it kind of captures the sentiment of like moving forward. And I'm not sure if you'll catch Nate's presentation, but he said, the goal of a race car is to accelerate in the most correct direction all of the time. And yeah, I mean, I just wanted that in the quote. All right, so let's see what happens. Let's talk about moving forward or accelerating in the right direction. This is what we see. We see the throttle pedal. It's the right pedal in the cockpit. And when we press it some distance, Mark 5 goes forward. That's great, like, cool. That seems pretty simple, but let's look a little bit deeper and see what's actually going on here. All right, so let's just take a look at this real quick and we'll break it down. We have our pedal. It's sending some signal to our throttle board. The throttle is also receiving information from the BSPD or brake light board. The throttle is also receiving information from the dashboard or the driver UX board. And then the throttle is sending some signal to the motor controller. And the motor controller is requesting torque from the motor, making Mark 5 move forward. So yeah, I kind of represented these with green lines because that's how it is on the block diagram. These are communicating over CAN, and we'll get into that in a second. But let's start with the pedal. So if you've ever seen the pedal, you'll notice that there's two linear potentiometers here. And a linear potentiometer is basically a variable resistor. The resistance of this potentiometer changes with the amount that the pedal is being pressed. So let's take a look at this. I represented what our potentiometer sensing circuit looks like. We have 5 volts connected with a scaling resistor, a potentiometer, and then that goes to ground. What we're doing with the throttle board is reading basically how far we have the pedal pressed. And we have 2 different values for these potentiometers, which I'll get into in a second. But to make our lives easier, we just make the second scaling resistor like a 0 ohm resistor. And as we know, a 0 ohm resistor is basically a wire. So let's express it like that. All right, cool. What does that mean? Basically, we can map some pedal travel, sorry, it's covering it up, some pedal travel to some output voltage that we're reading on the throttle board. So when we push the pedal this much, we'll see 2 different voltages out. And that's because we have 2 different scaling resistors here. That's just changing the transfer function. It's changing how the voltage out is being scaled. Cool. We have these 2 values. After we get them, we do a little bit of math, and then we basically undo the scaling for one of them so that they both line up perfectly. And you might be thinking, great, like why do we do that? We just added a second transfer function and now we have these 2 things and now we're redoing some extra work to do all of this. The reason that this is so valuable is because what if there's a problem with our signal lines? What if both of our voltage outs are shorted to the same value? If we don't have that transfer function and we don't undo it, the car will just think we're like full throttle potentially. And that could potentially be very dangerous or disastrous for anyone in the vehicle or around it. So this is a really good safety check. Also, it adds some redundancy to our system. So if one potentiometer breaks, there's also another one there. But if one of our potentiometers breaks, we should stop the vehicle. Okay. It's also told in the rules that we want to check for implausibility in the APPS, which is the pedal position sensor, which is basically the potentiometer. Yeah. So let's just take some time and have a quick quiz. I just launched a poll. Hopefully y'all can see it. Okay, looks like most people have voted and everyone got the answer right. It is to ensure a reliable analog signal for our pedal travel. Great. So let's zoom back out and look at the next step. Let's look at the dashboard. So the driver UX is sending some information over CAN to the throttle board. So the dashboard is constantly checking for certain conditions to be met. And when these conditions are met, the dashboard will send the ready to drive or RTD signal to the throttle over CAN. So this is kind of what it looks like. The dashboard has a checklist. It has 3 checks to be specific. And when all 3 checks are met, it'll say, okay. And when it says okay, it'll send okay over CAN. Throttle will get the okay message and it knows that we're ready to drive. What that means is that we can start sending torque requests to the motor controller. What that means is basically when we press the throttle some, we'll get a response from the motor. We'll be able to move. So those 3 steps that I mentioned, there's 3 of them. This is what needs to happen to enter RTD. We call it the startup sequence. There's no value prop for this startup, but there are these 3 steps. 1, we must successfully complete pre-charge. 2 is we must engage the brakes. And 3 is we must press the start button. So if y'all have driven Mark IV or an earlier vehicle, you'll remember someone probably told you, press the brakes, press the start button, and you'll hear the sound. That's basically the same thing here. And what these 3 things are checking is, the first one is seeing if the vehicle is ready to go. That's what pre-charge is doing. Next, the brakes and the start button, it's checking to make sure the driver is ready to go. So once we know that the vehicle and the driver are ready to go, then we can enter RTD. Then we can start requesting torque. Then we can start moving. Cool. I'm going to come back and talk about pre-charge in a bit because it's super important. But quiz time. What are the 3 checks for RTD? And I'm going to send out a poll. Okay. Alrighty. I think that's mostly everyone. And everyone got it all right? Yep. Pre-charge, brakes, start button. Good job, y'all. All right. Also, feel free to stop me if you have any questions at any point, especially during these during these quiz slides, because it's a good kind of lull in my quick presentation.
Audie, can I ask a quick question?
Yeah, go for it.
In your schematic that included the potentiometers for the brake, you said that there was like 5 volts at the top. Does that happen on the throttle board, or does that happen elsewhere, like near to the brakes?
Yeah, good question. So these are the throttle potentiometers. So it's actually the accelerator pedal, not the brake pedal.
Yeah, that's what I meant.
Yep. But we're supplying the 5 volts and 0 volts from the throttle board. And then we're reading this output voltage. It's a 3-wire connection that goes to the potentiometer here.
Okay, cool.
Yep. Okay, back to this. So now let's just pretend we're RTD. The throttle can send torque requests to the motor controller. Cool. But also the brake light BSPD board plays a little role here, and let's just chat about that real quick. So at the heart of this kind of statement, the brakes are more important than the throttle. Like I'd say 99 times out of 100, it's probably safer to be stopping than to be moving. If the brakes are pressed, we want the throttle to stop requesting torque from the motor controller. So we sense when the brakes are pressed. We have an analog pressure sensor inside our brake lines, and it detects when the pressure increases when you press the brakes to a certain point. And once we've crossed that threshold, the car knows the brakes are pressed. When the brakes are pressed, the throttle will say, whoa, we don't want to go. So I'm going to send a 0 torque request, meaning we don't want to be moving to the motor controller. So yeah, there is like this little nuanced rule that says if both pedals are pressed more than 25% pedal travel, we must cut power to the motors. And that power must remain off until we lift the throttle pedal all the way up past 5% before we get actuated again. Yes, you may have experienced this state when you were driving Mark IV or whatever vehicle, and it's not a bug, it's a feature, because the brakes are more important than the throttle. All right, quiz time. So true, false. If you press both the brakes and the throttle, and you have to disengage the brakes and lift the throttle all the way up before you could request more torque.
Sorry for the weird line endings on this one. I guess I didn't do a very good job.
Audie, I have one more follow-up question.
Yep.
Why is it that we have the two potentiometers on the throttle and not the brake?
Sure. So we actually don't have a potentiometer at all on the brake. We have no way of knowing exactly how far the brake pedal is being pushed from like just the distance we've pushed it. We have a pressure sensor in the brake line, and that pressure sensor is detecting the current, or it's checking the pressure in the brake line, and it has some corresponding output value to that. So when you apply more pressure, the voltage out of your sensor increases. So once we've crossed a certain threshold, we'll know the brakes have been pressed. We don't really care how far the brakes are pressed. We care if the brakes are being engaged, if the driver is trying to engage the brakes mechanically.
And then where are the brake pressure sensors located?
That's a good question. I actually don't know exactly where it is on the car, but it's in line with the brake fluid loop.
Cool, thanks.
Yep. Okay, so let's just talk about this poll real quick. So yeah, because of this rule, we want to lift the throttle pedal all the way back up before we engage it again. If our brakes are still past 25%, the throttle is going to cut out again, because this first part of the rule says that if they're both engaged past 25%, the brakes are going to take over. So we do want to let off the brakes. We also do want to let off the throttle before we apply it again. Just wanted to clear up any possible confusion there.
I have a quick question about one of your previous slides. Can you go back a couple to the one with like the boards, the fake boards?
Which one? This one?
Yeah, that one. Okay, so just to clarify that I'm like not confusing it, the driver UX is responsible for starting the car, right? And then the brake light is responsible for stopping the car, and it's all affecting the throttle.
So there's several conditions that need to be met to start the car. Like we have those little master switches, those keys that you see the ESO's turning every now and then. I don't think we could generalize saying start the car with the driver UX board, but it does tell us when we're ready to drive. And ready to drive means we could start sending torque requests to the motor controller.
All right, okay. Got it.
Yep. Okay. So now let's just look at the throttle sending torque request to the motor controller. And the motor controller is probably the biggest black box we have on the electrical system for this team. Lucky is probably the most well-versed with it, but there's a lot of documentation for it. There's a lot of stuff we don't really know about it, but we know enough about it to make our car run. But there's always more to learn. So I like this meme. I thought it was funny. So this is kind of like what an interaction between the throttle and the motor controller looks like. And let's just fix some of the words a bit. So the throttle says like, give me torque. And the motor controller is like, okay. And then the motor, like delivers the torque. It moves the vehicle. Yeah, that didn't really add too much value to the presentation. I just thought it was funny. Okay, so to go from pressing your throttle pedal to seeing a moving vehicle, there's all of these intermediate things going on. And all of them, every single one has to be met before that throttle is being mapped to some torque and we're seeing motion. Okay, great. We're pressing the pedal and now Mark V is moving. But I left out an important detail. Where is that power coming from? What's kind of sourcing the current needed to deliver the torque? Where does HV come from? How do we go HV? Those are excellent questions. And to answer that, let's talk about public transportation, namely the T. So this is the red line. You may or may not have taken it in Boston. And let's modify it a little bit to kind of see what I'm getting at. Okay, now it's purple. I remember seeing that purple somewhere before. I'm not sure if y'all do. Purple line, shutdown circuit, something, yeah. Oh yeah, there it is. You can see that it's looks kind of different than this weird like nodes going everywhere. It looks more linear. And this is a more accurate representation of the shutdown circuit. If we're like a train, we have to pass through every stop before we could go further. If the train breaks down in the middle, it's not going to get past here. And that's kind of the same thing for the shutdown circuit. Great, what does that mean? So let's say we have a 12-volt battery instead of a train, and we're trying to drive some circuitry. Like we need to deliver current to something. Oh, look at that, the airs. So we have the air plus and the air minus on kind of the split out point on the T. And I'll talk about that split in a second. And if you want to be more accurate, there's actually not any more stops after you hit this one. When it branches out, it goes straight to the airs. And that'll make a lot of sense in a second, but just bear with me. So cool. We have our 12 volts and we need to pass every single stop in order before we see 12 volts at this node, which the air plus and air minus boards feel. Okay, and this 12 volts is going through the shutdown circuit. Okay, so you've heard me say the word air a lot. You might have seen the airs. You might have heard people talk about air control, air mount, air whatever, right? So, whoops, I messed up the timing of my slides. So we have 12 volts going to the airs, and this is the actual shutdown circuit. So each of these little like T-stops is actually a node where it's like a switch or a relay or something. And eventually we get to the end and it splits off to your air plus and your air minus. Okay, now what is an air? Air stands for accumulator isolation relay. They're these like massive relays, they're like this big, that basically serve as gatekeepers that allow high voltage to be present outside of the accumulator. They're kind of like what holds the power inside of the battery pack before we know it's safe to supply power to the motor controller, to the motor. We have two of them, one on the plus side of the battery and one on the minus side of the battery. That's really all we need to know for right now. So let's just take this information and run with it. Also, if at any point you feel lost with the acronyms or whatever, you forgot what BSPD stands for, that supplemental document has all the abbreviations, so you could refer to that. Okay, so quiz time. What happens if we activate or open the shutdown circuit? What happens if the train breaks down in the middle of it? I'll give you a little bit of a hint. We need the 12 volts to power the airs, to make them close. So if we activate or open the shutdown circuit, if there's a problem, what happens to the airs? And I'm going to send a little poll here.
The ESOP is really just a kill switch.
Mm-hmm.
It destroys the entire.
Okay, I'll wait a few more seconds and then we'll move on. It looks like there is more than one person who thinks that the driver will explode if you activate the shutdown circuit, which makes me concerned. I think we have to go back and just restart the presentation now. So let's go back to slide 1 and talk about why the driver will not explode when we activate the shutdown circuit. Just kidding. Yeah. If we activate the shutdown circuit, we cannot close the airs. And if we cannot close the airs, that means that high voltage won't be present outside the accumulator. It's like the ultimate safety check. The shutdown circuit, all those stops on the train station, all those train stations need to be passed, all those safety checks need to be passed before we can close the airs, before we let high voltage be present outside the accumulator. Okay, let's go through a crash course of the shutdown circuit, because I'm sure y'all have all heard like many of these like words before, and I just want to shed some light on them. So first, let's talk about the GLVMS and the TSMS. So that stands for the grounded low voltage master switch. The TSMS stands for the Tractive System Master Switch. Tractive system is our word for high voltage after the airs. So the high voltage inside the battery pack, inside the accumulator, that's HV, that's high voltage. But everything after the airs, so after we close the airs, all of that high voltage stuff, it's the tractive system. So it drives the motor, it goes to the motor controller, stuff like that. Okay, words out of the way. They're the two like car keys you see on the side of the vehicle. That's what we really do to like start turning the vehicle on, in a sense. So the first stop in our shutdown circuit is the GLVMS. And the last stop is the TSMS before we go to the airs. We'll come back to the TSMS, but first you turn the GLVMS. That lets 12 volts from the battery go and start reaching the shutdown circuit. The next stop are the E-stops. They're the two red buttons you see on the sides of the vehicle here. It's so that someone can shut off, de-energize the vehicle if there's a problem. Next is the BSPD. And we talked about the brakes, but we didn't really talk about the BSPD. So let's take a minute to kind of look at this. BSPD stands for Brake System Plausibility Device. And what it's doing, it's checking to see if the driver is in control. And let's see what that means. Okay. This is what the circuit looks like. And these are some waveforms which I'll explain in depth right here. So let's look at a graph, okay? We have time versus an output voltage. So we know when current is going to the motor. We have this thing called a current sensor, and it detects when current is flowing to the motor. When current is flowing to the motor, that means we're requesting torque. That means the throttle is probably pushed, and that means that the car is moving forward if we're delivering current to the motor. So we have this thing called the current sensor, and when we're requesting power, when current is going to the motor, your output will be some value. It'll be like high. It'll be 5 volts or whatever. Current is flowing to the motor when we see this value being high. Okay, we also know when the brakes are pressed because we have a different sensor. We see when we've pressed it past a certain point, if there's enough pressure in the brake lines. So if we see a high output for the brakes pressed, power should be cut to the motor. Remember that rule we talked about earlier? When the brake is 25% pressed, power is cut. We're not going anywhere. Cool. We also have this thing called a BSPD relay. This is the part of the shutdown circuit. The relay will close if everything is good, allowing 12 volts to be present on either side of it, or it'll be open if something's bad. 12 volts will not be present after the relay. So on is good, off is bad. So we turn it off if things are not going well. All right, cool. So let's say current's flowing to the motor, and let's say the driver hits the brakes. Power should be cut to the motor, but uh-oh, this is still high. This value, it got hidden here, but it's still high. What that means is that the driver no longer has control. It means that they are pressing the brakes, but the motor is still like drawing current. We're still moving forward even though the brakes are being pressed. That's a very dangerous situation to be in because when you're trying to stop, it's probably for a good reason. If we hold the state where power is going to the motor and we're trying to stop the car with the brakes in that state for longer than half a second, we're going to activate the shutdown circuit. We're going to open the BSPD relay. So if the driver is out of control, meaning that if we're pressing the brakes and the vehicle is still moving, we de-energize the vehicle. We open the BSPD relay. Hopefully that made sense. All right, quiz time. What is the BSPD checking for?
So the 0.5 seconds, does it usually come to that point where the BSPD has to be activated? Or is that like how it stops? Or is it usually that the brakes can't control it?
Sure. I'm not sure if I quite got your question, so I'll just explain a little bit of stuff and then let me know if I answered your question. So normally when we press the brakes, we detect that the brakes are being pressed, the throttle will say, okay, I'll get out of the way. And we stop requesting torque from the motor controller.
Is that like instantaneously?
Yeah, it's
Okay.
basically instantaneous. I don't know exactly how long it is, but it's very fast, much less than 0.5 seconds.
Okay. So like BSPD is like a second check.
The BSPD is like the end all be all. Like if for whatever reason we're pressing the brakes and we're still moving, it's like, no, this car is not safe. And then
Okay.
we shut down.
I'll also add in, since I did a lot of work on this board, that we actually have a BSPD test switch because we can basically never get this to work. So we need a way to actually be able to test to make sure that in the rare occasion that it does happen, that we can actually shut down the car. So we also have like the BSPD test switch, which is, I think, rules required because you need to have a switch to make sure that your circuit will actually work eventually.
Okay.
What the BSPD test switch is taking the function of is the BSPD current sensor. It's just shorting 5 volts to the BSPD. Yeah, I mean, there's a circuit that I don't want to get into the weeds of, but it takes in 2 inputs. It takes in whether the brakes are pressed and the current sensor. And the test switch is basically pretending like the current sensor is outputting a high value. Okay, moving right along, let's take a look at the cockpit area. We have 3 nodes in the cockpit area. First one is the inertia switch. And it's this little yellow baby rattle thing you've probably seen in the LPB. I'm sure most of y'all on the electrical team have probably like just played with it or fiddled with it. It's kind of cool. It's like a spring-loaded ball. And when the sensor experiences some high amount of force or acceleration in some direction, it'll open the switch. So you can think about that like if our car crashes, we're going to accelerate in a negative value very quickly. Something crashes into our car and we accelerate to the side or something. That's very bad. I don't know exactly what that value is, but it's pretty high. But it's pretty cool that we could recreate it with our hands. Yeah. Next up is the brake over travel switch, or the BOTS. And what that's checking is, do our brakes actually work as intended? So like, let's say you're pressing the brakes. What happens when you press the brakes is you increase the pressure inside your brake lines. And that makes your little brake clampy things, I don't know what they're called, clamp down on the brake disc. And that makes your wheels like mechanically slow down. But if for whatever reason we lose pressure in the brake line and we press the brakes and it's not increasing the pressure, not clamping down on those brake discs, the car's not going to slow down when you want to. So we detect that with literally like an on-off switch. So if the brake lines lose pressure and you press the pedal and there's no pressure, the pedal will go way further than it normally does. So we just kind of embed this guy like back here. And if we lose pressure in the brake line, this switch will trip and we know the brakes don't work anymore. And then we'll shut down the car. That's what the BOTS are. Finally, driver emergency stop. It's the little red button over here. Same story as the other emergency stops. It's just a button. Cool. So those are the 3 in the cockpit area. Next, we have the high voltage disconnect, or HVD, the connector to the HVD, and the main pack connector, or the MPC. Again, all these acronyms are on that supplemental document, so don't be worried if you don't remember what the MPC is. Basically, they're these huge orange connectors. They're rated for like high voltage, high current. They're like touch safe. Yeah, if they're disconnected, we can detect that. And if they're like not engaged or in properly, we won't be able to close the shutdown circuit. We won't be able to drive the errors. So like last year, it was on the back of the accumulator. This year, it's more like behind the seat. So this is this year's accumulator. This is the connector to the HVD. This is the main pack connector. They're like over here somewhere. Cool. All right, quiz. How many nodes are in the cockpit?
I don't think I made this one. Sorry.
Okay, Lucky didn't make this one, so I'm just gonna give it to you. It's 3. Cool. Any questions right now?
Yeah.
Oh,
So
sorry.
when you say
Go ahead.
When you say like a shutdown node, that's not a board, right? Like those are just like the actual physical switches.
Yep, it's the switches or the relays or whatever it is.
Okay.
And in the example of the like HVD main pack connector, like the high voltage connectors, they have another set of contacts that's very small that you can't really see well. That's a low voltage contact. So that's like physically disconnecting the circuit. It's not like a switch or relay. It's like you're pulling a piece of metal out of the circuit when you disconnect the connector.
Yeah, I'm not sure how well you could see it on here, but like there's two tiny little holes that are where those metal contacts Lucky was just describing live. Yeah, okay. All right, final stretch of the shutdown circuit. The airs are in sight. Woo! All right. So we've gotten past these big connectors, and now we've hit the battery management system, or the BMS. The BMS is checking every cell voltage, and we have a lot of cells. It's checking the cell temperatures of like clusters of cells to make sure that no cell is overheating. It's also making sure that we're not dumping too much current into the pack or drawing too much current from the pack. If anything bad is happening to our battery pack, the BMS will open the shutdown circuit because every single cell is extremely dangerous, and we have like 900 of them inside our battery pack. Very dangerous thing. So we want to make sure that our battery is safe. That's why we have the BMS. Next, we have the IMD, or the Installation Monitoring Device. It's checking to make sure that high voltage is not shorted to low voltage at any point in the car. So a little bit of perspective for why that's a bad thing. Our low voltage system, or the GLV system, grounded low voltage system, is grounded to the chassis. The chassis is very easy to touch. So let's say that high voltage is shorted to our GLV system, and you grab one end of the chassis and your hand bumps into the other, or you kick the corner of the chassis or whatever. Now you have high voltage potential across you. So that's like 400 volts across your body, which has a regular resistance of like 100,000 ohms or something. If you do the math, the amount of current flowing through your body is still more than enough to kill you. So it's extremely dangerous. We don't want high voltage potential to be present like somewhere where people can touch it, because that's very dangerous. You can die or get very, very hurt. So that's what this thing's checking for. Very important. And then we end up with the airs. We have a plus, like high side air, and a low side air on each side of the battery. There's also this discharge relay and pre-charge relay, which I'll talk all about in a second. And you can see that we have the air control board, which is kind of controlling one of the airs. It's also controlling the pre-charge relay. The discharge relay and the other air are being driven directly by the shutdown circuit. Don't sweat the details about this right now. Okay. So you're probably saying, so what? Like, what's the point of the shutdown circuit? The answer is the shutdown circuit drives the airs. And if high voltage can't pass through the service section, it's not present outside the service section, excuse me, unless the airs are closed. If there's no high voltage present on our tractive system bus, there's no power there. If there's no power, we can't drive the motor. If we can't drive the motor, we can't go. So yeah, if we can't close the airs with the shutdown circuit, we won't be able to drive the car. This is just a little interlude if you're curious about where the airs are. So I said it's the last stop in the accumulator. So this is the accumulator, and these are our segments. And over here is a service section. It's like this last kind of front section here of the accumulator. And in there live the air plus and the air minus. So they're like I said, the gatekeepers that go to these two huge connectors that supply power to the motor controller. You might be wondering how I know the airs are there. It's kind of like this weird funky eyes shape. It's easily identifiable, like on this trash can, which I found once. I thought it was cool, so I put a picture in. Okay, another quiz. What do the airs do? So, do they air out the dust settling on the motor controller? Do they check for isolation between high voltage and low voltage? Or are they the gatekeepers? Okay, it looks like we're mostly right. So someone did respond, I'm sorry to out them like this, but we do not air out the settling dust in the motor controller. And I'm sorry that it's come to this point, because if you don't understand why we close the airs, I'm gonna have to rewind and go through the entire shutdown circuit explanation again.
Wait, so
Let's
then
start-
I'm confused. So what do we do with all the dust?
So the dust, I don't want to say anything that I'll have to cut out when I upload this video. So I'm not going to say anything dumb right now. All right, great. The airs are driven. Let's go. Let's drive Mark 5. Let's revisit the startup sequence. Still no value prop. So the 3 conditions. We need to complete pre-charge. Remember, we saw that pre-charge relay kind of hanging around in the shutdown circuit earlier. The driver must also engage the brakes, and the driver must engage the start button. These 2, I want to think, are pretty self-explanatory. So let's focus on pre-charge. What is pre-charge? To answer that, let's go back to the block diagram. And let's strip away some of the details a little more. Before we do that, let's talk about the motor controller. So we have our accumulator. It has a lot of power in it, high voltage. And let's say we close the airs immediately. What we see is high voltage present here, and it flows through this loop all the way to the minus side of the battery pack. When you have high voltage and very little resistance, if you think about the airs, there's like a relay. So maybe there's some resistance in like the contacts, but it's relatively low. So if you remember Ohm's law, V equals IR. If you have a low resistance, the current's going to be pretty big if the voltage is big. And if you have a massive current going into the motor controller or anywhere, that's bad. You might be saying, why is a lot of current going to go into the motor controller? Well, let's take a deeper look. Inside the motor controller, there is some capacitance, 440 microfarads to be exact, or pretty close to that value. I'm not sure if that's like actually discrete capacitors or the capacitance of the wires inside the motor controller. I'm not sure, but that's not important. There is some capacitance that needs to be charged up. And if you remember our capacitor equation, the current flowing through the capacitor is equal to the capacitance times the change in voltage over the change in time. If you think about it, we're going from 0 volts to 400 volts over a very small amount of time. When the airs are open, there's 0 volts at the motor controller. When we close the airs, 400 volts on the motor controller. And your capacitor is like a wire, basically, when you first connect it to your circuit. So the resistance is like nil, very small resistance. So you have a massive current and a very low resistance. If you think about it, the airs are in series with the motor controller. So as this capacitor is drawing a shitload of current, the airs are going to be experiencing that amount of current flowing through them. Now let's think about the airs real quick. So I just cleaned this up a little bit so it's easier to see. We have a lot of current just going through this series circuit here. The airs are like a physical component. They're rated for some current, and it doesn't matter what that number is right now. The point is, if we're dumping like a ton of current through them, we have those metal contacts. What happens to metal when you pass current through it? It gets hot. When metal gets hot, it has this tendency to melt. And if the metal kind of like melts and welds itself together, all of a sudden our airs are welded shut. That means that we won't be able to open them. That means that high voltage is present outside the accumulator. That means our gatekeepers have failed. That's extremely dangerous because we'll never be able to open the airs if they're welded shut, unless you like open the air up and you like unweld it. But that's besides the point. Okay, so what can we do to mitigate this huge inrush of current going to the motor controller? Well, let's put a current limiting resistor in it. And we call this the pre-charge resistor. So what I did here was I broke this connection to the air, and I added this relay here with this resistor. And these are being controlled by the air control board. Don't worry about the details on that. But we've added this resistor, and it's limiting the current going to these capacitors. So nice. Now we have much less current because it's limited by a giant resistor here, flowing here, and our errors are safe. Everyone's happy. We have successfully pre-charged the capacitors inside the motor controller. Nice. So that is where HV comes from. That's where the high power is coming from. We close the airs, allowing high voltage to be present outside the accumulator. When that's true, our tractive system bus has access to power. When we request torque from it, current will flow to the motor. When there's current flowing to the motor, it'll produce torque, we'll move forward. Okay, another quiz. Why do we have a pre-charged circuit?
Does the air controller boards, are they the ones responsible for breaking that connection with the air and then making it into the high voltage, no, not high voltage, high resistance one?
Yeah, so the air control board, there's one of them. It does break that connection. So if I go back here, yeah, the air control board controls whether this relay is closed or open. So if you think about it, when this pre-charge relay is open, current will not flow through this resistor. It doesn't want to flow there because this is like infinite resistance when this is an open switch. Same story for this air. When the air is open, current will not flow through here. And if we close the pre-charge relay when this is open, we force the current to go through this limiting resistor.
What if the air plus was also closed? So if the air plus and the pre-charge relay is closed, which one has less resistance?
The air plus will have way less resistance. Like this is like
Okay.
a 10,000 ohm resistor. This will be like on the order of like ohms or milliohms, like tiny.
Okay. So they're definitely never both closed at the same time.
Yeah, you really don't want them to be closed at the same time.
Okay. Makes sense.
Yeah. Okay. So yeah, I'm not sure. Yeah. So we have a pre-charge circuit to safely charge the capacitance in the motor controller. Charging the car is what we do like when the accumulator is outside of the car. We have a charging cart that handles that. And the airs are, if you remember their name, accumulator isolation relays. So relay is just like a switch. So we don't really need to charge those. We just need to power them maybe with the shutdown circuit, but there's no charging really happening there. So yep, just to reiterate, pre-charge circuit, charge those capacitors inside the motor controller safely. Okay, we're done. That is like good. Let's turn off the car now. Oh, we forgot. There's still those capacitors in the motor controller, and capacitors like to hold on to charge. They don't want to let it go until they absolutely have to. And now they have to. And there's still like high voltage, 400 volts like in these capacitors ready to just go and, dump a bunch of current through whoever wants to grab either end of them. So what do? We have to discharge those capacitors. So we have pre-charge's cousin, the discharge circuit. So let's zoom in a little more. Let's clean this up and boom. We have the discharge relay and the discharge resistor. Similar principle. So let's pretend that we've opened the shutdown circuit. If you'll take a look here, I took out the HVD. Sorry that this thing popped up, but I opened the HVD. Or let's say we hit the E-stop. Something happened, the shutdown circuit's open. Now that the shutdown circuit is open, the airs aren't being driven. The airs are open. But we still have these capacitors ready to be discharged. So we have a relay that discharges all that excess power. Now you might be asking, how does this relay know to close? And that's a good question. This relay is what we call normally closed, which means that when it's not being powered, it's gonna be closed. It'll be like a closed switch. And this is being driven by the shutdown circuit. So if you think about it, when we have 12 volts present on one end of the coil, that normally closed relay will actually open up. It's an open switch now. Since it's an open switch and the shutdown circuit is closed, current will flow like nice willy-nilly through our airs through the motor controller, and the discharge resistor will be ignored. But as soon as we open that shutdown circuit, that relay is going to go back to being closed because it's not being driven anymore, and that'll allow all this excess energy stored in these capacitors to just dissipate. It's kind of like a cool down lap. There'll be like a little current loop here, and then eventually no power left. Yep, so yeah, this is just kind of a cleaned up view of that. This resistance value is also massive, so you dissipate a ton of power across it, and your current will be very manageable, very small. Okay, another quiz. I know it's a lot, but hopefully these are helping you all make more sense of these topics. So why do we need a discharge circuit? All right, looks like mostly everyone has responded. The answer is we want to dissipate the residual energy on the TS bus. So if you remember what TS is, it's all of the high voltage potential post airs. And we have those high voltage potentials on those capacitors inside the motor controller, which is part of the tractive system bus, or TS bus, and we want to dissipate those. So our discharge resistor is giving us that cool down lap, discharging those capacitors. So the answer is to dissipate residual energy on the TS bus. We do not want to discharge the accumulator because that'll be annoying, especially if we want to turn the car on again in a short period of time. Also, since the connection to the airs are broken, the pack is isolated. Like it's not in contact with anything. There's nowhere for that power to really go. It's like a battery that's just, hanging around. Cool. Yeah, I mean, that is like Mark V, what makes it turn on, how we go, kind of how we stop also. And as you can see, there's a lot of other stuff there. Maybe I only talked about like 3 or 4 boards, but every single board is doing something that's enhancing the vehicle. Like a lot of the boards in here are helping with debugging. The cooling and temp pressure is helping with sensing. In the same vein of sensing, we have sensing modules where there's like literally like wheel speed, tire temperature, suspension strain, those kinds of things. Yeah, I mean, there's a lot of stuff going on. So that was an electrical overview of Mark V, but before we're done, I just want to jog through the block diagram one more time. Let's turn on Mark V. Let's say we want to go. Let's say we want to drive. What do we do? So we just have our stuff, chilling. Let's turn the GLVMS. If you remember what it is, it's the first car key, the grounded low voltage master switch. As soon as we turn it, 12 volts is present on all of our low voltage boards. They start their operations, they're doing their thing. When that happens, the CAN bus comes online. So all these boards start talking to each other. At the same time, a lot of the communication for like analog values or sensing or whatever, those come online too. The last thing that comes on when we turn that GLVMS, if you remember that T diagram, boom, shutdown circuit. So we're doing all these safety checks. We're checking the e-stops, we're checking the, BMS, IND, all of those things. And then to get high voltage present, to close the airs, we have to turn the tractive system master switch, the second car key, kind of like the last stop on our shutdown circuit. So we turn that, we have high voltage present, but no current is going to the motor yet. And that's because we haven't gone RTD. Remember, there's 3 steps to RTD. Let's say pre-charge is done. Let's say that's all done and good. Next, we want to press the brakes. Driver press the brakes, great. Driver press the start button, great. The driver's ready, the car is ready. You'll hear the kind of annoying RTD buzzer go off, and boom, you have your current going to the motor. You can request torque. That is Mark V in a nutshell. So yeah, that's all I have for you. I know that was a ton of information, but hopefully demystified kind of how different pieces of this puzzle fit together. And I'll just leave this open for any last minute questions.
Thanks, Adi.
Yep, thank you.
Thank you.
I'm going to stop share so we can see each other. You also don't have to ask me questions about the car. You can ask me questions like about my day or like, you know, what my favorite color is, or
Adi, what's your favorite color?
I'd have to say
Still
it's like
my
a nice like stone gray, you know?
Okay.
A quick question. What is the meaning of life?
That's a good one. And as my time as E-Lead, it really it gave me a clear answer to it.